Okay, thanks everyone for coming. I would like to thank the organizer for putting together this wonderful workshop during the marketing week. So, yeah, I'm not going to march meeting this time, but I'm pretty glad I still have some activities to participate. So today I will talk about quantum Hall states or fractals, or more precisely, I will talk about quantum Hall states with a conserved dipole moment. Before we proceed, I would like to thank my collaborator. This is still an ongoing project, and it was initially proposed by Hata Lam, who was a postdoc at MIT and Eastern Lake, a final year PhD student at MIT, and also with collaborating with Professor Jin Han, who was primarily in Sokwang University in Korea, and last year he was sabbatical at MIT and Harvard. So today I will talk about some interesting analogies or extensions for quantum Hall states. So before we proceed, I would like to have a 1-minute overview on what we know about quantum Hall state, although I believe most people in this room are more expertise on this topic rather than me. So if we have strongly interacting electrons combined in a 2D quantum wire with Coulomb interaction subject to a strong magnetic field, we find that at certain fields, the electrons can form an incompressible state where the charge degree of freedom inside the bulk are fully gapped. What is interesting is at the boundary, there turn out to be some chiral charge degree of freedom that is moving along the single directions at the boundary, which is a concrete manifestations of the current anomaly on the boundary. So today we want to talk about whether there are any interesting generalization or extensions of such kind of quantum Hall phenomenon. So in a few words, the essence of quantum Hall zoology is that we have strongly interacting system where the bulk degree of freedom is incompressible and the charge carrier turn out to be gapped. However, the boundary degree of freedom turn out to be gapless, and it is more than gapless. So the boundary would carry a certain type of anomaly with respect to the symmetry. Like for most quantum Hall state, what would happen is the charge U1 degree of freedom and the bulk are fully gapped, but at the boundary, we have a U1 current anomaly. And they also have quantized electromagnetic response that is pretty immune for strong interactions and disorder. Today, what I want to talk about is we want to generalize such type of quantum Hall phenomenon into fracton systems. More precisely, we want to seek whether there are any quantum Hall-like phenomena that can appear in a system with dipole conservation. So what is dipole conservation? Yesterday, actually, Dan Song already mentioned dipole conservation. So let's have a brief overview of the definition. So in usual system, when we consider a charged insulator or some type of many-body physics with charge degree of freedom, we have a usual U1 symmetry such that the total charge number in the whole system have to be conserved. However, we can also imagine there is a system which has both charge conservation and a dipole moment conservation. On lattice models, the precise definition of a dipole moment is the sum of all of the charge density at a certain locations times its position operators. And if we have a system where both the charge and the dipole moment cannot be conserved, we can imagine that the elementary charge carrier would exhibit some fracton dynamics because a single charge carrier cannot move alone. So in a usual charge conserved system, the simplest dynamical term we can write down is something like a charge boson Hopin term, where we create a charge at some site and annihilate it at nearby site. So such kind of Hopin terms do preserve the global charge conservation, but it will definitely change the total dipole moment of the system. So imagine if we have a system where we need both charge and the dipole moment to be conserved. We cannot create a single boson and let it move in any direction. No matter how you move it, it would change some type of dipole moment in a certain direction. Instead, what we need is we need a charge and anti-charge forms a pair, like a dipole moment where we have a charge particle and anti-charge particle. And this dipole moment that has a certain type of orientation because the charge and anti-charge turn out to be spatially separate with a lattice unit cell or something like that. This charge neutral object can either fluctuate in the transverse direction, like we create a particle hole pair and let it fluctuate in a perpendicular direction, or it can move in the longitudinal direction, such that we create two charge bosons at a site and annihilate the charge from the left and from the right. So such kind of dipole, here I will call it dipole U symmetry that corresponds to the fact that its dipole moment is also conserved. Such dipole U symmetric system is actually widely observed in many body systems, like simple and not simple, concrete example with what Stan Soong talked about yesterday. If we consider a quantum Hall effect on the vortex lattice, what would happen is the boson operator, the phase of the boson operator is somehow locked with the gradient of the lattice displacement. And because of that, the dynamics of the boson should also exhibit a dipole symmetry. So when we write on the kinetic terms of the boson, it turns out that it has a quadratic dispersion that is akin to some type of Lie-Shih theory. So this is one of the concrete manifestations where we have emergent dipole U symmetry in a strongly interacting system in 2D. Another typical setting to realize dipole U symmetry was first proposed and realized in AMO system mainly by Monica from Technical University of Munich. And what they do is on an optical lattice, they will put a very strong linear potential, a strong electric field in one direction. And they consider the two Fermi-Hubbard chains with such kind of linear potential. Because of the strong linear potential, a single charge operator would not be favored to fluctuate in a 1D chain. Otherwise, you will suffer from a very strong energy penalty because of the strong electric field. Instead, we can have some charge neutral object, like here the blue corresponds to the charge and the red corresponds to some anti-charge, forms a dipole moment. And this neutral object does not perceive the linear potential in 1D. And these are the elementary degree of freedom that can fluctuate in a 1D tilde Fermi-Hubbard chain. And in addition, in concrete condensed matter system, which was pretty well known, if we consider the quantum Hall state on a thin torus in the lowest lambda limit, such kind of system also exhibit a special type of dipole U symmetry, because once we consider the quantum Hall state.
So this system, if the tilde is very strong, the ground state obviously will be all the particles stacked at one side of the system.
True.
So in what sense is the dipole symmetry going to be relevant here? So I guess certainly we are not going to look at the ground state.
Sure, they are not looking at the ground state, and actually their experimental setup is they want to look at the non-equilibrium dynamics with dipole preserved symmetry. At the low energy, it is pretty trivial. It's just have all of the charge concentrated at the lowest potential site.
Okay, yeah, I think one single process will have a very fast oscillation in time, and the other, if you come back, maybe it will cancel out this oscillation. Yeah, maybe that's the case.
So if we consider the quantum Hall state on a thin torus limit and project them to the lowest lambda level limit, we can see that the Hamiltonian effectively preserves the dipole symmetry, because if we choose the Landau gauge, the momentum in one direction is somehow locked with the position operator. And once you project it to the lowest Landau level, what would happen is, because of momentum conservation and because of the fact that momentum is somehow locked with the position, momentum conservation automatically means that you have dipole moment conservation, or in the quasi-1D limit, it's almost something like the center of mass conservation. And hence, if we write down the quantum Hall state on a thin torus in the lowest Landau level limit, what we can see is that we don't have a fermion-Hopkin operator. Instead, we only have a full fermion operator where we create two in the center and try to annihilate one and the other one at the left and the right side.
Okay. What happened to other conditions? So in that picture, like you have a really fun condition, right? Like then.
No. So actually, I should put something like a thin cylinder instead of a thin torus.
Oh, I see.
And actually, you're correct. If here would omit the boundary condition problem, because whenever you have periodic boundary condition and for a U1 dipole moment that turn out to be ill-defined, since you cannot.
So every time you discuss dipole symmetry, you are assuming like an open boundary condition.
Yes.
Huh. Okay.
So the outline of today's talk is we want to figure out what type of quantum Hall phenomenon can exist in a dipole preserving system. And what do I mean by quantum Hall phenomenon is that we have some type of degree of freedom, and in our case, it is both charge and the dipole moment that turn out to be incompressible and has a finite gap in the bulk. However, at the boundary, they are gapless and exhibit a certain type of perturbative anomalies. And the second question is, what type of anomaly can emerge on the boundary of a dipole quantum Hall effect? And what are their electromagnetic responses, whether they have a quantized electromagnetic response or not? And finally, we would like to explore whether it is possible to write down some type of field theory of such kind of dipole quantum Hall state, and whether we can generalize such kind of quantum Hall state in other special symmetric system, like apart from dipole symmetry, we can consider whether we have a quadrupole symmetry and so forth. So our primary aim is to consider a quantum Hall state with a conserved dipole moment. And to begin with, let me be less ambitious. I want to make the case simple. So let me think about a simple case, which is somehow anisotropic. So I'm considering a system which has charge conservation, and I only have one dipole moment conservation. I only require that the dipole moment in the x direction to be conserved. That's it. The theory will be highly anisotropic, but this might be the simplest case I can start with. So that says we need to have charge conserved and dipole moment conserved. So if we have a charge carrier that's now to be a boson, the typical kinetic term I can write down is, since I only require the dipole moment to be conserved in the x direction, such kind of boson can fluctuate and hold along the y direction. However, when it comes to the x direction, the boson charge carrier itself cannot fluctuate. Instead, the leading order term need to be something like this, where we have a dipole moment and we let it fluctuate along the x direction, or we can think about something like create two charge boson in the center and pump a minus E charge and another minus E charge here. So how to imagine there is some type of quantum Hall state exist in this dipole preserving system where we only have dipole moment px to be conserved. So again, you may ask, what do you mean by quantum Hall state, quantum Hall-like analogy in dipole preserving system? So for me, the simple and transparent phenomenon for quantum Hall is that for quantum Hall, we only have charge U1 symmetries. The charge degree of freedom are incompressible and fully gapped, but at the left and right boundary, there turn out to be a current anomaly of the U1 charge. So if we put it on an open cylinder and insert a 2-pi flux, the left chiral boson would acquire one charge, and the right chiral boson propagating in the opposite direction would lose one charge. So literally, once we insert the flux, we will have a charge pumping from the left to the right boundary. And on each boundary alone, it would exhibit some type of current anomaly. However, if we combine the two boundaries and the bulk system as a whole, it should be anomalous. Okay, so based on this, maybe we can have some intuitive guess on what does it mean by a dipole quantum Hall state, or what can we expect how to imagine something like a quantum Hall state in a dipole preserving system. So for quantum Hall state, it's a charge insulator, but at the boundary, the charge exhibits a current anomaly with a chiral charge current. And a naive and intuitive hunch, which may not be correct, but let me just put this hunch here, is for a dipole version of the quantum Hall effect, in the bulk, both the dipole moment and the charge degree of freedom are insulating, it is fully gapped. However, at the boundary, we can have a chiral dipole current.
So can I ask a very simple question? We have dipole in the magnetic field, they want to move in opposite directions. So how does that work with the dipole?
Okay, so good question. So here, what I'm talking about is quantum Hall analogy. It is true that when we have quantum Hall state, we need to put it on a strong magnetic field. So we have lambda level and flat band. That is why interaction finally plays a role. But in order to reach, have a quantum Hall phenomenon, it is not necessary to have net magnetic field. In principle, we can have something called Chen insulator where there's no external magnetic field penetrating the lattice. However, as long as you break some time reversal symmetry, you can still have some depth of bulk with an insulating degree of freedom and a chiral current at the boundary in the absence of magnetic field. And this is what I'm considering. So this is a naive hunch. And let's first check whether this is possible. So what does it mean by a chiral dipole current? So let me sketch a picture like this. Suppose we have a boundary which is terminate along the x direction. So the boundary is along y direction. And we have both charge and x dipole moment conserved. What I can imagine for a chiral dipole moment is that at a terminate boundary, say at the first row, at the first row, there turn out to be a left moving mode. And on the second row, which is spatially separate with the first row, it's still localized boundary, but it's spatially separate with one line of spacing. There is a left moving mode, or we can imagine this left moving mode as an anti-charge moving in the right direction. So as a whole, this is something like we have a charge and anti-charge that are moving chirally along the y direction. So suppose we have some type of chiral dipole current localized at boundary, and we want to figure out is first whether such kind of pattern is possible in nature. What I mean by possible in nature is on a pure 2D lattice model with only local interaction, whether we can realize them or not. So in order to figure out what are the consequences of an insulating state with a chiral dipole current, what I can imagine is I can insert a flux and see what is the total response under a flux insertion. So suppose let me make the y direction periodic. And here we still have charge U1 symmetry. We can insert a flux with respect to the charge U1 symmetry by shifting the gauge potential A1 with a constant.
Sorry, shouldn't the other boundary have opposite arrows?
Yes, sorry.
Okay.
Yeah, so what would happen is it's pretty straightforward. Once I insert a current and here I have a left moving mode, it will acquire E charge. And this left moving mode would annihilate minus E charge and the opposite for the other type of boundary. So literally such kind of flux insertion would create a dipole moment at the boundary and create an anti-dipole moment at the other boundary. So this is one consequence which seems to be correct and there's nothing abnormal here. However, remember the system I'm talking about has both charge conservation and dipole moment conservation. The dipole moment oriented in x direction is also conserved. And as Damso mentioned in his previous talk, if we have a dipole moment conservation, we have another U1 symmetry where the chiral boson are invariant under a shift, which is not a phase shift, which is not a constant, but instead it's a function that grows linearly with the position along the x direction. If we have dipole moment conservation, the boson field would be invariant under such kind of phase shift. And for such kind of dipole, let me just for the dipole U1 symmetry, we can also create a flux with respect to this dipole U1 symmetry. And the setting is that along the we can insert a 2 pi flux along the y direction that is equivalent to create a gauge potential that is not a constant. Instead, it grows linearly with the x position. And what does it do? So suppose we assume that the bulk degree of freedom are fully gapped for both the charge and dipole carrier, so probably nothing would happen. However, such kind of chiral moving mode at the boundary would respond. And for this pattern, because we insert a dipole flux where the momentum shift grows linearly with the position X, what would happen for the first row is we insert a 2 pi flux, and for the second row, the chiral boson proceed 4 pi flux, and same for the final row, it creates a flux that is 2 pi times L. And if we have a dipole, chiral dipole current and anti-dipole current, what would happen is that we have a left moving mode and 2 pi flux will create E charge. And this is right moving mode, and creating a 4 pi flux would annihilate minus 2 E charge and so forth. And for the other boundary, if we have a left moving chiral boson, creating a 2 pi times L flux would annihilate minus E times L number of bosons charge. And then what would happen is, after such dipole U1 flux insertion, we can count what are the change for the total charge charge and for the total dipole moment. So here I'm not just counting the change of the boundary. Instead, I'm combining the top and bottom boundary and bulk as a whole and see whether the total charge and the total dipole moment are invariant under the whole system after we insert such kind of one dipole flux. And here's the thing. Just by some counting, the total charge is invariant under the flux insertion. However, the total dipole moment for the whole 2D system is not invariant under the flux insertion. So here's the obstruction. If we assume that such kind of phenomenon can exist in a 2D lattice model with local interaction, the minimal requirement is that it needs to be anomaly free, which means we have a certain symmetry. Here is the U1 charge symmetry and U1 dipole symmetry. After flux insertion, the total charge and total dipole moment should be invariant under flux insertion. Each boundary can have some anomaly, but if you count all of the boundaries together with the bound as a whole, they should be anomaly free. Unfortunately, if we have such type of settings such that we have chiral dipole current and anti-dipole current localized at the boundary, what would happen is inserting a U1 flux with respect back to the dipole symmetry would make the total dipole moment not invariant after this flux insertion or large gauge transformation. And that says such kind of phenomenon is anomalous and cannot exist in a pure 2D system with only local interaction. So from this story, it turns out that we can talk about a simple no-go theorem. Intuitively, if we have a quantum Hall state for a charge carrier, we know that the charge degree freedom are fully gapped in bulk, and in the boundary we have chiral charge. But this does not extend to dipole or even quadrupoles. If we have a system with dipole moment conserved, it is impossible to realize a chiral dipole current at the boundary, provided that you are dealing with a pure 2-dimensional system with local interaction only, because such kind of phenomena would be anomalous in the bulk. Okay, so now I see that our primary hunch is not correct. And then the second question is, if this is not correct, then what type of quantum Hall-like phenomenon can exist in a dipole conserving system? Or what type of boundary can exist? So now let's not make an assumption. Let's just be general. Suppose we still have some type of interesting quantum Hall phenomenon in a dipole conserving system, which means the bulk degree of freedom are incompressible, everything is gap, but we still have some type of gapless degree of freedom. I don't know what other settings, but there are some gapless degree of freedom on boundary which turn out to be anomalous on each boundary alone. So let me just make an assumption that there are some chiral current on the first row with M1 central charge. So there are M1 number of chiral boson moving along the left. And if M is positive, that means left. If M is negative, that means I'm moving to the right. And same for the second, there also turn out to be some chiral current. I don't know how many of them, and I don't know their direction. So let me just write down M2, which is the central charge, and positive and negative correspond to whether you are moving to the left and to the right, and so forth. And same for the other boundary. There are some type of chiral current localized at boundary. I only plot 2, but there might be 3 or 4 or even more, but there must be finite because I assume that the gapless degree of freedom have to be localized at the boundary. So suppose this exists, then what type of M1 and M2 patterns, chiral boson patterns, can appear at the boundary? So to be precise, we know if I say such kind of phenomenon can be realized in the 2D lattice model, P2D lattice model with only local interaction, everything should be anomaly free. And here we have two types of symmetry. One is the charge U1 symmetry, the other is the dipole U1 symmetry. And anomaly free means that it is anomaly free with respect to the U1 charge conservation. That means if I insert a U1 flux, say in the y direction, then the total charge in the whole system need to be invariant after flux insertion. And this requires that sum of m need to be 0. So there's no net chirality. And it should also be anomaly free between the mixing anomaly of the U1 symmetry and U1 dipole symmetry. If I insert a U1 flux with respect to the U1 dipole symmetry, I still require that after flux insertion, the change of the total charge need to be invariant, and the change of the total dipole moment should also be invariant. So these are the three primary requirements of the choice of M we can choose as the boundary. So in principle, there are a infinite number of choices you can make, although much of which are equivalent. So let me go into the simplest choice.
I here is lattice side.
Yeah, so I correspond to the x equal I, the x position. So the simplest choice I can imagine is that we have 3 rows of the with gapless degree of freedom localized at the boundary, and same for the other 2 with opposite chirality. And what happened at the top boundary along the y direction terminate at x is at the top row, x equal 1, we have a left moving mode. On the second row, we have c equal -2. So we have 2 left moving mode localized at the same x position. And on the third, we again have a right moving mode. So this is more like a quadruple current localized at the boundary. So this is one of the possible patterns we can imagine. And the problem is now what we demonstrate is from anomaly-free condition, we know such kind of boundary could exist, but how can we fulfill such type of boundary state? And in particular, like for fractional quantum Hall state, we have a lot of possibility. We can just put the electrons in a 2D quantum while subject to magnetic field, and as certain feeling we get it, we can fabricate some type of Chen insulator and to realize it. And in order to have a concrete manifestation of such type of boundary state with a dipole preserving Hamiltonian, what I will implement is the coupled Y construction. So let me be brief. So coupled Y construction is just a typical way for us to construct the gap topological phase, mainly with chiral boundary or helical boundary in 2 dimensions from 1D Latinger liquid. So imagine we have a set of Latinger liquid and we align them along the x direction. For each 1D Latinger liquid, we can decompose them to the left and right moving mode. And all we need to do is for the left moving mode on the first row and the right moving mode on the second row, we can couple them and introduce backscattering to gap them out. And we do the same in a translation invariant way. What would happen is all of the helical Latinger liquid are coupled, have interwire coupling between different rows, and they're fully gap out. The only remaining mode that is not gap out is one of the, if we have open boundary condition, the left mode, which is up moving, and at the other boundary, the right mode, that is down moving, remain gapless. And that literally becomes the fractional quantum Hall bulk with a chiral current localized at the boundary. So now let's do the same thing. In our system, what we have is we require charge to be conserved, and we require the dipole moment along the x direction to be conserved. So I can align some type of Latinger wires along the y direction, because in the y direction, the boson can fluctuate as normal. So I have a set of wires along the helical Latinger liquid along the y direction. And for each row, I put 4 copies of them. So we can somehow write them in terms of 4 copies of the helical fermions with different flavors that localize at the same row. And here, what we want to do is we want to couple them in a way such that the bulk degree of freedom turn out to be truly gapped, and we do have some leftover degree of freedom in the boundary. However, the subtlety is that the system is not just the conserved charge. We also need to conserve a dipole moment along the x direction. And that says for these, if we write down the fermion, left and right moving fermion in terms of the chiral boson, all of these chiral bosons are invariant under a shift that grows linearly with the x position. And we need to couple them in a way that respects such kind of dipole symmetry. And that means it is impossible to have an interwire coupling that just backscatter one fermion from the top to the other fermion on the bottom. Such kind of scattering term will definitely break the dipole U1 symmetry. So in principle, we need at least something like a full fermion interaction terms to preserve the dipole U1 symmetry. And that also means that such kind of system does not have any non-interacting fermion or band theory analogy. So in order to manifest such kind of couple wire construction, we probably want a building block. So the building blocks contains some type of chiral fermion from different rows. Here I have a chiral fermion on the first row and from the fourth row, and also 3 chiral fermion and anti-propagating chiral fermion from the second and third row. These building blocks, them, has interwire coupling, which respect the charge and dipole symmetries, and the bulk degree of freedom is just a translation of these building blocks. And because the interaction only appear within the same building block, all I need to do is figure out a symmetric way that can gap out all of the gapless degree of freedom in the building block. Then I can manifest that the bulk degree of freedom can be fully gapped. And here the only subtlety is that for all of these chiral fermion, apart from the fact that they all carry the same U1 symmetry, they also carries a dipole U1 symmetry where the charge of that dipole symmetry do depend on their position. And hence, what we need to do is we need to have something like a full fermion interaction terms where we create 2 left moving bosons from the central row and annihilate a right moving boson and another right moving boson at the top and bottom row. So this is one of the interaction which can respect the dipole U1 symmetries. And here in each building block, we actually have 4 helical mode in total. So in principle, we need 4 independent mass terms to gap out everything. So then just after some algebra, we will figure out that all of the commuting terms of these backscattering terms, and only 4 of them are independent. So these terms would fully gap out all of the degree of freedom in the building block. And finally, what would be left over is at the first row, if we have a boundary, we'll have a chiral fermion that is not coupled with any of the building block. On the second, we have 2 chiral fermion moving in opposite direction that is not coupled with any of the rest of the system. And same for the third, we have a chirocentric charge 1. So this boundary literally look like a chiral quadruple current. First, this is gapless, but how do we know it is anomalous? Because in principle, we have 2 left moving mode and 2 right moving mode. However, if we have a dipole symmetry, one can demonstrate that there is no way for you to fully gap out the gapless degree of freedom at the boundary. Because for such type of boundary, if I insert a U1 dipole flux, what would happen is the H dipole moment at the top boundary and the bottom boundary would not be invariant under the flux insertion. Them as a whole is still invariant, but each H exhibits a self-anomaly under the U1 dipole symmetry, and hence there's no way for you to gap out the boundary degree of freedom. And same if we try to write down the equation of motion of the boundary, we can figure out that the boundary do behave like a quadruple moment, where we have a typical setting of the quadruple is we have charge 2e in the center, and the top row we have a charge e, and at the bottom row we also have a charge e. This is something like a quadruple moment in electromagnetism. And
for your system, do you even have quadruple conservation?
no, I don't.
So what does a quadruple current mean then?
So the quadruple current means that we have charge 2e in the middle and e and minus e and at the top and bottom, and they move currently along one direction.
But just to make sure, you're not saying the quadruple current forms some conserved current.
No, no. we have a chiral quadrupole current with this setting that is moving chirally along one direction. So, okay. So now up to this stage, we figure out a concrete manifestation of the fractional of the quantum Hall state with dipole moment conservation via couple Y constructions. And one may ask, what are the, can you figure out all of the possible quantum Hall states with dipole moment conservation? And what do I mean by quantum Hall state here? Again, that means that the charge and dipole carrier turn out to be fully gap involved, but there turn out to be some gapless degree of freedom localized at the boundary that is guaranteed because the boundary has a certain type of anomaly. So in order to characterize or classify the possible quantum Hall state for dipole preserving system, it is equivalent to classify how many anomalies can appear on the boundary if we have both charge conservation and dipole conservation. So here on the boundary, for the whole system, we have two types of symmetries. One is the charge U1 symmetry, and the other is the dipole moment is conserved. So in principle, we can have three classes of anomalies that can appear. So the first is the self anomaly of the U1 current, and that says if I insert a flux, 2-pi flux with respect to the U1 symmetry, on each boundary, the charge is not invariant under flux insertion. This is similar to the usual quantum Hall state. And the other is a self anomaly for the dipole U1 symmetry. This is exactly what we just manifest a moment ago via coupled Y construction. If I insert a flux with respect to the dipole symmetry on one of the boundary, the dipole moment on the boundary turn out to be not invariant under flux insertion. So there's a shift of H dipole moment under such flux insertion. This is a self anomaly with respect to the dipole symmetry. And in the meantime, we can also have a mixing anomaly between the two. That says if I insert a dipole U1 symmetry, the boundary, one of the boundary turn out to have a shift charge density under dipole U1 flux. This turned out to be a mixing anomaly between the U1 symmetry and the U1 dipole moment. And what we find is that previously our couple Y construction manifests one of the phase which only have dipole anomaly, and the other two possibility is that we have both dipole self anomaly and mixing anomaly between these two, or we can have phase where all of the three anomalies do exist. However, remember here there's a hierarchy structure. If you recognize that at the boundary, you have a U1 current anomaly, it is required that the mixing anomaly and the dipole anomaly must be presented. And same, if we don't have U1 anomaly, but we have mixing anomaly, it would be required that the dipole self anomaly would also need to be presented. It is impossible to have mixing anomaly and U1 anomaly alone. So why is that? This actually is based on the definition of charge, dipole, and dipole moment. So from the anomaly equation at the boundary, what we can see is that have a U1 anomaly, that means on one of the boundary, if we count all of the M as the center charge on different rows, the total charge need to be 0. And for mixing anomaly, it's something like the sum over dipole moment need to be 0. And this is more like quadrupole moment need to be non-zero. And this is for mixing anomaly that correspond to something like the dipole moment. For the dipole moment to be well-defined under any translation shift or to make it well-defined, regardless of which lattice, which coordinate you choose, we have to require that the total charge need to be invariant. And same.
No, can I view a spin as a magnetic dipole? Spin is like positive magnetic charge and negative magnetic charge.
Yes, but can you have that magnetic charge and charge being totally deconfined and spatially separate?
No, but the quantum spin Hall insulator will have like a
correct. So
right?
so this is similar to the quantum
magnetic dipole current.
spin Hall. That's we all have dipole mode. For quantum spin Hall, this is something like the left mode is spin neutral and the right moving mode carries SZ charge. And for
No, I'm talking about quantum spin Hall, not spin quantum. Quantum spin Hall is like a upspin moving to the right, downspin moving to the left.
yes.
So there's a magnetic dipole current as the boundary. So I wonder if that has to do with one of the bases here.
No, it has nothing to do because like the one spin Hall, what you can see is you actually don't have U1 current anomaly but you do have a mixing anomaly.
Mixing anomaly.
Yes.
Yeah.
And the problem here is if you have mixing anomaly, UR anomaly itself must be presented because for
Say again, sorry.
if you have mixing anomaly, then the UR anomaly itself must be presented. The dipole anomaly itself must be presented. So for you can say that okay, for spin we can imagine it's a magnetic monopole and a monopole is separated apart, but for that problem, the spin is an internal degree of freedom which commutes with any translation and rotation symmetry. It is really an internal symmetry. Dipole moment is not. And the dipole moment or dipole moment charge is not invariant under translation. And that also means that the dipole charge transform non-trivial under translation. So this is not an internal symmetry. And this should be pretty important when we think about other generalizations. So I should terminate at 10.
Yeah.
Yes. So let me talk about the summary and take home message. Today we talk about a concrete example of quantum Hall state with dipole preserving systems where the boundary carries some type of quadrupole current. And counterintuitively, while a charged quantum Hall state means have a charge insulator with a chiral charge current, a dipole version of quantum Hall state does not allow you to have a chiral dipole current at the boundary. If this appears, the whole boundary of freedom together with the boundary would be anomalous. And such kind of novel theory can also be generalized to other multiples like a quadrupole or even octupole. If we have a system with conserved quadrupole moment, what I can say is it is impossible to have a chiral quadrupole moment at the boundary, at each boundary. Otherwise, such kind of system would again be anomalous as a whole. And in principle, we can generalize our couple Y construction to fractional case by couple fractional Latinger liquid, and eventually we can get some analogy of the fractional quantum Hall effect with a dipole conserving symmetry. And so let me summarize some of the open questions. So since we can consider the couple Y construction from fractional Latinger liquid, in principle, we can obtain the dipole version or dipole symmetric fractional quantum Hall state. An open question is how to write down the effective theory, like a high rank symmetric Chern-Simons type of gauge theories for such kind of fractional quantum Hall state. And these states will turn out to have some type of UVI mixing because in principle, the ground state degeneracy will depend on the system size. And in addition, an important signature of the dipole or quadrupole symmetry is that this is not an internal symmetry because the symmetry generator does not commute with translation and rotation. And hence, they are very sensitive to some lattice defect. So for a dipole moment, for charge that carries a dipole moment, if we place a charge at position X versus X2, it carries different type of dipole moment. So suppose we introduce something like a dislocations and disclination that turn out to be the lattice defect of translation and rotation. What we can foresee is that these lattice defect will somehow permute different topological quasi-particle type or anion type because the presence of dislocation is something like I stick a dipole moment at X and dipole moment at X plus 1 together. And these lattice defect can, in principle, carry some additional zero mode and form a projective non-abelian defect. The third open question is we have a couple Y constructions for a dipole symmetric quantum Hall state. And in order to make an analogy between the normal quantum Hall state versus the dipole invariant quantum Hall state or quadrupole invariant state, it will be interesting to figure out whether we can develop some type of anion condensation transitions or anion condensation web to systematically link the normal quantum Hall state with the quantum Hall state with a dipole or even multiple conservation. So I think I'm running out of time, and finally, let me just take questions and thank my collaborators.
Let's see a few more words about the fractional case actually. So then you will need to turn on interchain coupling, but it will need some degeneracy. Is that right?
Yes.
But so does the degeneracy increase with the system size? When you increase the X direction?
So here there are two types of subtleties. And first is if we want to talk about ground state degeneracy, we have to put it on a closed manifold. But for dipole symmetries, sometimes it can be ill-defined up to when you have periodic boundary condition. And so then let me be simple. Let me just not look into the U1 symmetry. Let's look into something like the Zn symmetry by making n pretty large, and I can define the Zn version of that dipole symmetry. And then what you will find is, yes, that do depend on the system size, and usually for dipole Zn symmetry, it will depend on the greatest common divisor between the n of your Zn symmetry versus the system size Lx and Ly. Because once you drive a Wilson line operator and you want it to close, whether you can close or not usually depend on the system size, and otherwise you have to find their GC.
Right, so it does not increase indefinitely. with
True.
increase
So it's
size.
different from Fracton where
Yeah,
it's
right,
scales sub-extensively in systems. And also it depends on the orientation of your close, whether you close along X or Y direction or you close along the diagonal and the off diagonal, because for these type of quasi-particles, some of the Wilson line cannot bend. It can only go along the X direction, but cannot bend into the 45-degree direction.
Other questions?
When you were presenting the counting of the currents and cancellation of the total anomalies, it seemed like you had a system of three equations where there could be many, many different solutions. Yet you didn't consider those general solutions. You went to a specific example. Are there other more perhaps interesting solutions?
Yes. So in principle, we have infinite. In principle, we can have, because all I need is we have some integer number, positive or negative of m, and we only have finite number of them that are non-zero, localized near the boundary. We have an infinite number of solutions. However, among these infinite number of solutions, there are only 3 classes. And these 3 classes correspond to the type of anomaly you can have. Like today, the simplest solution is we only have self-anomaly, but we can have mixing and self-anomaly and the 3 anomaly together. However, we only have 3 classes, but we have infinite number of solutions. What does that mean? That means different type of boundary can correspond to the same anomaly. And that says even we can have, say, another different boundary patterns that correspond to the same self-dipole anomaly. There might be some additional gapless mode that is more non-localized at the boundary. However, first, this mode can be fully gap out without breaking any charge and dipole symmetry. Or these type of gapless mode are not protected by symmetry because they don't exhibit any anomaly. In principle, we can have some edge reconstruction to annihilate them.